Infinity, a word that drifts through the human mind like a shadow, vast and unending. It is the horizon that always retreats, the number that cannot be counted, the silence that cannot be filled. For most of history, it belonged to philosophy and theology, an abstraction invoked in paradoxes and prayers, but never in the hands of science. Yet, in the modern age, humanity has dared to build machines that reach for it. Great rings of metal beneath the earth, accelerating particles until they shatter into fragments of pure mathematics. Telescopes balanced on mountain tops and drifting through the void, pulling faint light from galaxies at the edge of visibility. Supercomputers that breathe in equations and exhale whole universes, simulated across eons longer than the life of stars. And still, infinity resists. The closer science approaches, the more it dissolves into contradictions. Black holes whisper of infinite density. The Big Bang hints at infinite compression. Equations collapse into infinities that must be cancelled, patched, or ignored. Infinity appears not as a solution, but as a fracture in knowledge, a place where mathematics reveals its own breaking point. The central machine is not a single device, but the collective effort of human reason, extending its reach through circuits, lenses, and accelerators. It is the attempt to measure the unmeasurable, to test whether infinity is a property of reality itself, or merely a reflection of the mind. What happens when science touches infinity? Does nature truly extend without end, or does infinity exist only as the ghost of human imagination? The story begins here, at the edge of thought, at the horizon of knowledge, with the machine that measures infinity. Infinity has always stood at the edge of human imagination. Long before equations carved the heavens, ancient thinkers gazed into the night and found themselves haunted by the unending. The Babylonians mapped stars across clay tablets, their patterns suggesting permanence without boundary. The Egyptians traced time in the eternal flooding of the Nile, believing cycles would turn forever. In China, records of eclipses stretched back millennia, hinting at a cosmos without origin. For the Greeks, infinity became a paradox that gnawed at philosophy itself. Zeno of Ilia, in the 5th century BCE, crafted puzzles that mocked human reason. A runner could never reach a finish line, he argued, for first he must cross half the distance, then half of what remains, and so on without end. Motion itself seemed to collapse into infinite steps. Aristotle distinguished between two forms of infinity, potential and actual. Potential infinity was a process, numbers that could always be counted further, divisions that could always be made smaller. Actual infinity, a completed endlessness, he denied to nature. Infinity, to the ancients, was not physical. It was the unreachable beyond. For nearly 2,000 years, this boundary held. The cosmos was pictured as finite yet eternal, a set of crystalline spheres circling Earth or, later, the Sun. To imagine actual infinity in the physical universe was heresy or absurdity. Even when medieval theologians invoked the infinite, it was not in matter or motion, but in God alone. Then came the 17th century. A new mathematics arose, calculus. Isaac Newton and Gottfried Wilhelm Leibniz, working independently, gave birth to a language of the infinite. By slicing time and space into infinitesimal fragments, they could describe motion, gravity, and light. The infinite was no longer abstract philosophy, but a tool of science. A falling apple, the arc of a planet, the pull of the tides, all could be expressed by equations that danced with infinity at their core. Yet for Newton, the cosmos itself was infinite, eternal, and absolute. Time ticked uniformly, space stretched without bound, and matter drifted within this infinite stage. Infinity had stepped from thought into the architecture of reality. The 19th century delivered a new shock. Georg Cantor, a mathematician of haunting brilliance, dared to compare infinities. He revealed that some infinities are larger than others, that the set of real numbers dwarfs the set of integers, and that mathematics is populated not by one infinity, but by a hierarchy without end. His discoveries shook philosophy to its foundations, igniting debates about whether infinity was real or only a trick of symbols. Cantor himself was tormented, spending much of his life in sanatoriums, consumed by the weight of his revelations. Infinity was no longer merely vast. It was structured, layered, terrifying. While mathematicians struggled, astronomers peered deeper into the sky. The invention of telescopes expanded the visible cosmos into a tapestry of countless stars. Galileo, in the early 1600s, turned his lens to the Milky Way and found it not a mist, but a river of innumerable suns. Infinity appeared to glimmer overhead, scattered in starlight. By the 19th century, many assumed the universe was eternal and infinite, a boundless sea of stars, without beginning or end. But cracks began to appear. Philosophers asked why the night sky was dark, if the universe truly extended infinitely. In space and time, every line of sight should end on a star. The heavens should blaze with light, without darkness. This paradox, known later as Olbers' paradox, whispered that infinity in the physical cosmos could not be real. Something was hidden. Something finite shaped the sky. The 20th century shattered all illusions of eternal infinity. In 1915, Albert Einstein unveiled general relativity, a new description of gravity as the curvature of spacetime. With it came a realization. The universe need not be infinite in space or eternal in time. Spacetime itself could bend, stretch, or collapse. Infinity was no longer a given backdrop, but a possibility to be tested. Einstein himself resisted. He believed in a static cosmos, eternal and unchanging, and introduced a cosmological constant to prevent collapse or expansion. But the equations themselves were restless, hinting at motion, not stasis. In the 1920s, Edwin Hubble, peering through the 100-inch Hooker telescope on Mount Wilson, discovered that galaxies are not fixed. Their light was redshifted, stretched. By motion, the farther a galaxy, the faster it recedes. Space itself was expanding. This single revelation altered the destiny of cosmology. If the universe is expanding now, it must once have been smaller, denser, hotter. The cosmos had a beginning, a moment of finite origin, not an eternal infinity. Infinity, once assumed, was dethroned. The universe was no longer timeless, but timed. Its age could be measured. Billions of years, not eternity. For the first time, astronomers glimpsed the possibility of an end, as well as a beginning. This discovery reshaped the very concept of scientific instruments as machines reaching for infinity. Telescopes were no longer devices for cataloguing stars, but probes into the past, each photon carrying a message billions of years old. Observatories became time machines, extending human perception toward the horizon of cosmic birth. The mid-century deepened this transformation. In 1948, George Gamow, Ralph Alpha, and Robert Herman predicted that if the universe began in a hot, dense state, it should still be filled with a faint afterglow, radiation cooled by expansion, stretched into microwaves. This prediction lingered until 1965, when Arno Penzias and Robert Wilson stumbled upon it with a radio antenna in New Jersey. The cosmic microwave background bathed the sky in a whisper of heat, a relic of a time when the universe was only 380,000 years old. The machine of science had touched something once thought infinite, the birth of time itself, from philosophy to mathematics, from Newton's infinite stage to Einstein's curved spacetime, from Hubble's expansion to the microwave. Echo of creation, infinity shifted from assumption to enigma. No longer the obvious truth of an eternal cosmos, it became a puzzle at the heart of physics. The machines of humanity, telescopes, accelerators, equations themselves were no longer charting an infinite reality, but circling the question: does infinity exist in nature, or is it only a shadow cast by the limits of knowledge? By the end of the 20th century, the stage was set for confrontation. Black holes promised infinities at their centers. The Big Bang pointed to an infinite compression at the beginning of time. Quantum mechanics stumbled upon infinities in its equations. Each machine built to measure reality, each telescope, collider, and computer found infinity not as clarity, but as breakdown. The discovery phase was over. Infinity had stepped from philosophy into physics, from abstraction into crisis. Humanity's machines had touched it, but what they found was not completion, but fracture, the beginning of a struggle that would define modern science. For centuries, mathematics had been the unshakable language of the cosmos. Its equations predicted eclipses to the minute, charted the tides, and guided spacecraft to the moon. Yet in the 20th century, something unsettling began to emerge. At the very boundaries of science's triumph, mathematics whispered a contradiction. It no longer revealed order, but broke into infinities. And when mathematics broke, it was not only equations that failed, it was the very picture of reality itself. The first warnings came from Einstein's own theory. General relativity, unveiled in 1915, had transformed gravity into geometry, the bending of space-time itself. It was elegant, powerful, and complete. It explained the orbit of Mercury, predicted the bending of starlight, and even suggested the possibility of black holes. But hidden within its equations lay a flaw. When enough matter collapsed under its own gravity, relativity insisted that space-time would curve without bound. Density would rise not to some extreme, but to infinity, at the center of a black hole. Einstein's mathematics predicted a singularity, a place where time ends. Space dissolves, and the equations themselves explode. For a while, these infinities were dismissed as mathematical curiosities. Surely nature would not allow reality to shatter. Yet in 1939, J. Robert Oppenheimer, long before the atomic bomb, joined his student Hartland Snyder to calculate the fate of collapsing stars. Their result was devastating. Relativity demanded singularities. A sufficiently massive star could not resist its own weight. No pressure, no force, no radiation could halt the collapse. Gravity would crush matter to infinite density. The singularity was not a trick of mathematics. It was the inevitable conclusion of Einstein's universe. This was the first true scientific shock. A physical infinity, lurking not in abstraction, but in the heart of dying stars. If singularities were real, then nature contained points where mathematics and perhaps meaning ceased to function. The second shock came from cosmology itself. In the 1920s, Edwin Hubble had shown that the universe was expanding. If expansion ran backward, everything must once have been compressed into a single point. Stephen Hawking and Roger Penrose, in the 1960s, proved that general relativity made this unavoidable. The universe began in a singularity. Time itself had an origin, squeezed into an infinite density at the Big Bang. Infinity stood at both ends of existence, at the birth of the cosmos and at the deaths of stars. Physics had always assumed infinities were signs of incomplete calculation, but now they defined the universe. The beginning and end of time itself were written as infinities. Quantum mechanics, rising alongside relativity, offered no escape. Built in the early 20th century, it revealed a world of probabilities, uncertainty, and wave-like particles. It was breathtakingly successful, explaining atoms, semiconductors, even the structure of DNA. Yet, when combined with relativity, it too stumbled into infinities. Calculations of particle interactions spiraled into endless values. Energies diverged to infinity. Probabilities lost coherence. To make sense of it, physicists developed a technique called renormalization, subtracting infinities in a way that preserved finite answers. It worked. Predictions became the most precise in all of science. The magnetic moment of the electron, calculated to 12 decimal places, matched experiment exactly, but the method was unsettling. Physics was not conquering infinity, it was hiding it, sweeping it under a rug of mathematical cleverness. Richard Feynman, one of renormalization's architects, once admitted that while the process worked, it was like sweeping dust under the carpet. Infinity had not disappeared. It remained an unresolved wound at the heart of quantum field theory. Then came an even deeper fracture. In 1974, Stephen Hawking combined relativity with quantum mechanics to study black holes. He discovered they were not eternal prisons, but radiated energy, a faint thermal glow, now called Hawking radiation. Over time, they evaporate, yet this raised a terrifying paradox. If black holes vanish, what happens to the information they contain? Quantum mechanics insists that information is never destroyed. Relativity insists that it falls into a singularity. Hawking's discovery forced the contradiction into the open. At the edge of black holes, the very horizons where relativity and quantum theory meet, the mathematics broke. Here was the second great scientific shock. Physics itself was divided. Two pillars of science, each triumphant in its domain, collapsed into contradiction at horizons where infinity intruded. This confrontation spread dread through the scientific community. Infinities are not just large numbers, they are the failure of theory, signals that the equations no longer describe reality. When infinities appear, it means the model itself is broken. The fear was profound. Perhaps at the most extreme scales, the laws of physics dissolve into nonsense, and the shocks kept coming. The expansion of the universe, once thought to slow under gravity, was discovered in 1998 to be accelerating. Type Ia supernova, exploding white dwarfs used as cosmic beacons, revealed that galaxies are not merely drifting apart, but rushing away faster and faster. This implied the existence of a new, repulsive energy, dark energy, filling space itself. With it came new horizons, beyond which light will never reach. Entire galaxies, and eventually clusters of galaxies, will slip away into eternal darkness. Time itself may stretch into an endless, empty infinity. This acceleration shattered the last hope of a static or cyclic cosmos. The universe was not only finite in age, but rushing toward a future where all but the nearest stars vanish beyond sight. Infinity had returned, not as singularity this time, but as a future of endless isolation. Everywhere scientists turned, infinity waited. At the core of black holes, at the birth of the cosmos, at the edge of quantum fields, in the accelerating horizon of dark energy. Infinity was no longer a mathematical dream, but a scientific nightmare. A paradox seared into the equations of physics. It was a profound shock to the philosophy of science. For centuries, infinity had been tamed, a servant of calculus, a background assumption of eternal cosmos. Now it emerged as a predator, devouring certainty. What does it mean if the universe begins with infinity, ends with infinity, and is threaded by infinities in between? Does this mean reality itself is infinite, or that the human language of mathematics has reached its breaking point? The shock of infinity reshaped cosmology into a field not of certainty but of crisis. Telescopes stared deeper, colliders smashed harder, computers calculated longer. But each breakthrough revealed not resolution but fracture. The machine that sought to measure infinity was not finding clarity, it was finding the limits of thought. And so, by the end of the 20th century, science stood in uneasy silence, the triumph of relativity, the success of quantum mechanics, the discovery of cosmic expansion, all seemed shadowed by equations diverged, paradoxes multiplied, and physics itself seemed incomplete. The shock was not only scientific, but existential. Humanity had touched infinity, and instead of enlightenment, found the boundaries of understanding. The next chapter of the story would not be triumph, but deeper pursuit, the search for what infinities mean, and whether they are true features of reality or mirages demanding new physics. The machine would be built larger, faster, more powerful. But what it sought was not simply measurement. It sought salvation from infinity itself. In the wake of scientific shock, humanity did not retreat. The appearance of infinity in its equations was not a deterrent, but a summons. Where mathematics faltered, instruments would be built. Telescopes, colliders, detectors, and supercomputers became extensions of human thought. Machines constructed not simply to observe stars or smash atoms, but to stare directly into the places where infinity lurked. If infinities were real, they must leave their mark upon the sky. If they were illusions, the machines might reveal the hidden scaffolding of a truer physics. The pursuit began underground. Particle accelerators, immense rings of steel and magnets, hurled protons to nearly the speed of light. In the late 20th century, machines like Fermilab's Tevatron in Illinois and later, CERN's Large Hadron Collider in Geneva became laboratories of the infinite. Their purpose was simple but profound: to recreate, in miniature, the conditions of the universe moments after the Big Bang. Collisions released energies far beyond anything natural on Earth, probing matter at scales so small that distances lost their classical meaning. Here, at energies approaching the Planck scale, infinities threatened to erupt. Quantum field theory predicted them. Renormalization tamed them. Yet physicists hoped that, beyond the haze of infinities, lay new particles, new symmetries, perhaps the very essence of reality. For decades, the search continued. And in 2012, one of the great triumphs arrived: the discovery of the Higgs boson. This elusive particle confirmed the mechanism by which matter gains mass. Yet even this discovery carried whispers of infinity. The Higgs field stretched across the universe, hinted that the vacuum itself might be unstable. If true, a deeper collapse awaited, a vacuum decay capable of rewriting physics at light speed. Infinity again loomed, this time as cosmic fragility. While accelerators searched inward, telescopes searched outward. The Hubble Space Telescope, launched in 1990, became a machine of infinities in its own right. Its mirrors gazed not only at galaxies, but at the very edge of time. Light from galaxies billions of years old crossed the void to strike its sensors, revealing a universe that was not infinite in age, but finite, with a beginning. Later, the Planck satellite mapped the cosmic microwave background in exquisite detail, the afterglow of creation itself, frozen from when the cosmos was less than 400,000 years old. Within its faint ripples lay the seeds of galaxies. The pattern was not random. It matched the fingerprint of inflation, a moment of expansion so extreme that in less than a heartbeat, the universe grew from subatomic to astronomical scales. Inflation was, in all but name, an infinite expansion compressed into an instant. These machines did more than measure light. They mapped horizons. They traced the boundaries of what could be seen, revealing that the observable universe, though vast, is not infinite. Beyond the horizon, space may continue without end, or it may curve back upon itself. No telescope can yet decide. Infinity hides just beyond vision. Supercomputers joined the pursuit, in sterile rooms filled with endless racks of processors. Simulations of cosmic evolution were born. Galaxies swirled, merged, and clustered across billions of simulated years. These digital universes revealed a truth. Without dark matter, galaxies would not form. Without dark energy, expansion would not accelerate. Without both, the cosmos would look nothing like our own. Infinity had insinuated itself into the calculations. Without infinite extensions of unseen matter and energy, the finite visible world collapsed. Meanwhile, observations of quasars, brilliant beacons, powered by black holes, offered laboratories at the edge of infinity. Their light, bent by the gravity of intervening galaxies, revealed the warping of spacetime itself. Gravitational lensing turned massive clusters into cosmic magnifying glasses, distorting images of galaxies behind them. In these distortions, astronomers saw dark matter itself, invisible, yet bending light as if it were a tangible presence. It was not infinity of number, but infinity of mystery. The cosmos was shaped not by the visible, but by what could not be seen. The Event Horizon Telescope, a planet-wide array of radio dishes, achieved what was once thought impossible. In 2019, it captured the first image of a black hole's shadow. A glowing ring of plasma encircled darkness itself, the horizon of no return. Here space and time curved to such extremes that Einstein's equations predicted singularity. The image was not only a photograph, it was a direct encounter with the frontier of infinity. For the first time, humanity had seen the outline of mathematics breaking down at the same time. Quantum electrodynamics, the most precise of all physical theories, confirmed both triumph and unease. By taming infinities with renormalization, it delivered predictions accurate to parts in a trillion. The magnetic dipole of the electron, measured and calculated, matched with eerie perfection. Yet beneath this success lay discomfort. The infinities had not been solved, only cancelled. The theory's power was undeniable, but its foundation felt fragile, balanced upon the subtraction of the infinite. Inflationary cosmology deepened the paradox. To explain the uniformity of the cosmos, physicists proposed a brief but overwhelming burst of expansion in the earliest instant of time. Space itself ballooned at a rate faster than light, smoothing the universe and seeding its structure. This inflation, if eternal, would never truly end. Pockets of space would continue to inflate, birthing bubble universes without end. Infinity was no longer a philosophical speculation. It became a physical consequence, written into the dynamics of space-mid. And so, the machine grew ever larger. Colliders hurled particles, telescopes pierced horizons, supercomputers modeled creation, detectors searched for the faintest ripples of gravity. Each discovery carried two messages: clarity and fracture. Yes, the Higgs boson exists, but it may imply vacuum collapse. Yes, black holes radiate, but this breaks the unity of physics. Yes, the universe inflates, but it multiplies infinities into uncountable worlds. By the close of the 20th century and the dawn of the 21st, science had expanded its reach beyond imagination. Yet the infinities remained. They were not illusions of ignorance. They were inscribed into the very fabric of equations, reflected in the very light of the cosmos. This was the deeper investigation. To measure infinity was not only to build machines of greater power, but to confront the possibility that infinity is woven into reality. And still, the question lingered: are these infinities real features of the universe, or signs that human thought has reached its limit? Are singularities true, or masks hiding physics yet undiscovered? Do bubble universes truly proliferate, or is infinity a mirage at the edge of comprehension? The machine had brought humanity to the threshold, but beyond the threshold, only mystery remained. Infinity is not a gentle presence. It does not wait quietly in the margins of equations. Once uncovered, it spreads, multiplying across the landscape of physics. What began as a few singularities in Einstein's equations has grown into a proliferation of horizons, paradoxes, and cosmic fates. The further science advances, the more deeply infinity entangles itself with the story of the universe. At the heart of galaxies lie black holes, not exotic exceptions, but central engines of structure. These immense objects, born of stellar collapse or seeded in the earliest epochs of time, bend spacetime into wells so deep that not even light escapes. Their existence, once doubted, is now undeniable. Yet with each confirmation comes unease. Black holes harbor singularities at their core, regions where Einstein's relativity demands infinite curvature. These are not hidden infinities confined to chalkboards. They are written into the sky, into the very centers of galaxies. Around each black hole lies an event horizon, a one-way surface, the border between knowable and unknowable. What falls through is lost to outside view, yet horizons themselves carry strange paradoxes. When Stephen Hawking combined relativity with quantum mechanics in the 1970s, he found that horizons are not silent, they radiate. Black holes slowly evaporate. But if they vanish entirely, what becomes of the information they once contained? Quantum mechanics forbids its destruction. Relativity insists it is gone. Here, at the horizon, two of humanity's greatest theories clash. Infinity is not a tool of prediction. It becomes the very mark of contradiction. The mystery deepens. Further, in the cosmos itself, observations of distant galaxies revealed that the expansion of the universe is not slowing, as once expected, but accelerating. Dark energy, an unknown force constituting nearly 70% of the cosmos, pushes space apart at an ever faster pace. The implication is staggering. There exists a cosmic horizon beyond which galaxies will slip forever beyond view. The more time passes, the more isolated our corner of the cosmos will become. Future astronomers may gaze at the sky and see only their own galaxy, the rest erased by expansion. Infinity emerges not as boundless abundance, but as boundless absence. These horizons multiply. There is the thermodynamic horizon of entropy, the inevitable drift toward maximum disorder. Stars burn, black holes evaporate, and the cosmos slides toward equilibrium, a heat death where nothing new occurs. This horizon of time stretches into near infinity, trillions upon trillions of years. Yet even if the cosmos lasts that long, the outcome is the same: silence, stillness, the end of novelty. There is also the horizon of inflation. If eternal, it ensures that beyond our observable bubble, other universes sprout endlessly. Some like ours, others alien beyond imagination. Infinity here becomes tangible, not a number, but a landscape populated by worlds without end. To describe the universe, cosmologists must speak of ensembles, of probability measures across infinities. It is not a comforting picture. It is a recognition that infinity may be the most real fact of existence, and yet infinities destroy. In calculations of quantum gravity, they appear without mercy, rendering predictions meaningless. In string theory, they must be avoided through higher dimensional structure. In quantum field theory, they are cancelled only through mathematical sleight of hand. Everywhere physicists look in black hole cores, in the birth of the universe. In the fabric of spacetime, infinities rise, mocking comprehension. This escalation transforms infinity from a concept into a threat. If infinities are real, physics itself may not be complete. If they are illusions, then the current framework of mathematics hides a deeper truth still unrevealed. Either way, the appearance of infinity signals crisis. In 2012, this crisis sharpened with the firewall paradox. If quantum mechanics is preserved, the event horizon of a black hole cannot be smooth, as relativity suggests. Instead, it might burn with unimaginable energy, incinerating anything that falls through. The horizon itself becomes a wall of fire. The paradox unsettled even seasoned physicists. If true, it would mean that black holes, once thought silent, are violently incompatible with the most fundamental laws of physics. Infinity here is not only abstract, but potentially catastrophic beyond theory. The very structure of the cosmos suggests limits we cannot cross. The observable universe is finite, bounded by the distance light has traveled since the Big Bang. Beyond lies territory forever beyond human reach. Even with infinite time, light from those regions will never arrive. It is a horizon in the most literal sense, a boundary inscribed by the laws of relativity. Infinity recedes as one approaches, unreachable, yet undeniably present. This deepening unease forces reflection. Perhaps infinities are not signs of abundance, but of breakdown markers, where current physics fails. Perhaps singularities are not physical points, but boundaries demanding new frameworks. Whether quantum gravity, string theory, or something still unimagined. Perhaps cosmic horizons are less about infinite worlds and more about the limits of perception itself. Yet, the more physics advances, the more horizons it reveals. The infinite is not avoided, but multiplied. Every theory, every observation expands. Its reach, relativity, once thought complete, leads to singularities. Quantum mechanics, once triumphant, introduces divergences. Cosmology, once finite, spills into multiverse. The closer science approaches understanding, the deeper infinity entangles itself. Emotionally, this realization weighs heavily. For centuries, science has thrived on the belief that reality is ultimately comprehensible, that with sufficient effort the universe can be written in equations. Infinity challenges that faith. If infinities are genuine, reality may not be compressible into finite descriptions. If infinities are illusions, then the very structure of mathematics is inadequate. Both possibilities confront humanity with the same conclusion. Knowledge itself may have horizons, and yet the escalation also inspires. To contemplate infinities is to recognize the audacity of thought itself. The machines, colliders, telescopes, detectors do not merely gather data. They extend the reach of the human mind into realms where intuition cannot follow. Each horizon is a mirror of limitation, but also an invitation to go further. In the silence of black holes, in the acceleration of galaxies, in the endless replication of inflation, infinity multiplies. It cannot be banished, only confronted. It is the ghost at the foundation of physics, the shadow behind every discovery by the early 21st century. The mystery was no longer confined to black holes or the Big Bang. It had become universal. Infinity was not a single problem. It was the pattern underlying them all. Horizons everywhere, limits everywhere. At each frontier, physics itself trembled, and so the story deepens. What began as paradox in mathematics has grown into a cosmic truth. Infinity is not distant. It is here, woven into the structure of spacetime. To understand it may require more than science. It may require a reimagining of what reality is. The escalation is complete. Infinity is no longer background. It is foreground. It is not philosophy alone, but experiment, observation, and data. The universe, it seems, cannot be told without it. If infinity is the shadow haunting every frontier of physics, then theories are lanterns, fragile, flickering, but luminous against the dark. Each attempt to tame the infinite is less an answer than an experiment in imagination. Theories are not merely calculations. They are bridges built from human thought, extending across horizons that no observation has yet crossed. The first great bridge of the modern age was relativity itself. Einstein's equations revealed spacetime as dynamic, elastic, capable of bending and collapsing. Yet it was relativity that also birthed the spectre of singularities, points where curvature becomes infinite. Einstein himself resisted these implications. He believed singularities must be artifacts, not realities. But as proofs by Penrose and Hawking showed, singularities are inevitable in general relativity. The equations of spacetime are not infinite in scope. They predict their own breakdown. Infinity here is not solved, but demanded to heal this fracture. Physicists turned to quantum theory. In the subatomic world, infinities appeared again, but renormalization allowed them to be contained. Quantum electrodynamics, perfected by Schwinger and Tominaga, could predict the magnetic moment of the electron to extraordinary precision. But the triumph was bittersweet. Renormalization did not eliminate infinity. It swept it under mathematics, leaving unease in its wake. Was the infinite a real feature of nature, or a flaw in the mathematics of fields? By the late 20th century, the search for unity led to string theory. Here, the point-like particles of quantum field theory are replaced with extended one-dimensional strings, vibrating in higher dimensional space. The beauty of this approach lies in its power. Strings, by their nature, diffuse infinities. They cannot be compressed to a single point. Their length softens singularities, spreading infinities into finite vibrations. Black holes, in this view, may not harbor true infinities at their core, but tangled webs of strings, resolving the paradox of infinite density. Yet string theory asks for a price. Extra dimensions, unseen and untested, curled away in scales beyond present detection. It offers elegance, but not certainty. Infinity is tamed in theory, but the machine of experiment has not confirmed. Its song, others pursued a different vision. Loop quantum gravity. In this approach, space-time is not continuous, but granular, woven from finite loops of geometry. At the Planck scale, space is no longer smooth. It is a lattice of quanta, like atoms of geometry themselves. In such a world, infinities cannot arise, for there is no continuum to collapse into a singularity. Black holes, instead of infinite cores, bounce into new regions of space-time. The Big Bang becomes a big bounce, a collapse of a previous cosmos reborn into ours. Infinity is replaced by cycles. But again, the theory remains speculative. The granularity of space is invisible at human scales, awaiting evidence from experiments not yet possible. Beyond quantum gravity, cosmology itself offers speculative infinities. The idea of eternal inflation suggests that the brief burst of expansion at the birth of the cosmos never fully ended. Instead, in distant regions, inflation continues endlessly, spawning bubble universes without end. Ours is one bubble, finite in age and horizon, but embedded in an infinite froth. Here, infinity becomes physical, not a breakdown, but an abundance. The multiverse transforms the question. Infinity is not failure, but excess, a universe too vast to ever be fully known. For some, this is liberation. For others, despair. If infinite worlds exist, then every possible history occurs somewhere, rendering our own existence both inevitable and insignificant. Alongside these grand vistas lies another radical idea, the holographic principle. Born from the study of black hole entropy, it suggests that the information content of a region of space is not proportional to its volume, but to the area of its boundary. In this view, the three-dimensional universe may be a projection of data inscribed on a distant two-dimensional surface. Infinities that plague quantum gravity might dissolve if the cosmos is holographic. What seems infinite in 3 dimensions could be finite when described on the boundary. Reality, in this model, is not broken by infinity, but reframed by perspective, other. Ideas venture further into the speculative. Could dark energy itself be tied to infinity, a vacuum energy field stretching without bound? Could the instability of the Higgs field signal that our vacuum is temporary, destined to decay into a lower energy state, rewriting the laws of physics at the speed of light? Here, infinity hides in fragility, the possibility that our universe, vast and seemingly eternal, is only a metastable phase. The infinite, in this telling, is not endless duration but the unbounded possibility of destruction. At the fringes, still more exotic speculations emerge. Mirror matter, a hidden shadow world interacting only through gravity, potentially explaining the mass of dark matter. Higher dimensional brains, our universe as one membrane in a higher dimensional space, infinities avoided by embedding. Even Digital physics, the idea that spacetime is discrete and computable, suggests that infinity may be an illusion, an artifact of assuming continuity where only finiteness exists. Yet, through all these theories, one truth recurs. Infinity is the signal of incompleteness. Whenever infinities arise, they are markers of physics pushed beyond its domain. Just as the ultraviolet catastrophe of 19th century physics foreshadowed quantum mechanics, so too may today's infinities herald revolutions yet unseen. Theories are scaffolds, provisional structures built until a stronger framework emerges. The infinite may be less a feature of reality than a signpost, pointing toward physics not yet written. Still, the philosophical tension remains. What if infinity is real? Cantor's infinities of mathematics may echo in the infinities of physics. An infinite universe, an infinite multiverse, an infinite stretch of time. These are not easily dismissed. They confront human imagination with its limits. To live in an infinite cosmos is to live in one where every boundary is provisional, every horizon only local. To deny infinity is to hope that nature is finite and knowable, that the machine of science can one day measure all, and so theories divide along this line. Some seek to erase infinity, to granularize spacetime, to soften singularities, to holographically encode the cosmos. Others embrace it, to multiply universes, to extend inflation without end, to weave infinity into the very definition of existence. Both approaches carry weight. Both reveal as much about the human mind as about the cosmos itself. Speculation, then, is not distraction, but necessity. Without it, physics halts at the edge of infinity. With it, the horizon becomes provisional, a challenge instead of a wall. Theories are the way science dreams beyond its instruments. They are how the machine, imperfect yet audacious, measures the immeasurable. For now, none are proven. Infinity remains elusive, but in its pursuit, science deepens, imagination expands, and humanity learns that the question of infinity is not just about physics. It is about what it means to exist in a universe where limits dissolve. If infinity is the horizon, then science builds ships. Each instrument is a vessel launched toward the unmeasurable, each designed to probe deeper, farther, closer to the places where numbers break. From underground caverns to orbital observatories, humanity has assembled a machine, vast and distributed, a collective instrument of inquiry, the machine that dares to measure infinity. It begins in tunnels carved beneath the earth, the Large Hadron Collider, a 27-kilometer ring beneath the fields of Switzerland and France, hurls protons into head-on collisions at energies once reserved for the heart of stars. In these flashes of violence, densities approach conditions of the early universe, fractions of a second after the Big Bang. The hope is not to create infinity, but to glimpse its shadow, to see where particle interactions break down, where theories predict divergences. If space and time have a granularity, if exotic particles such as supersymmetric partners exist, they may emerge here. The LHC has not yet found them. Its silence is telling. Infinity remains unmeasured, hiding at scales still beyond reach. Yet, the collider is only one voice in the chorus. Far above Earth, telescopes stretch vision toward the cosmos. The Hubble Space Telescope revealed that galaxies populate the universe like grains of sand on a shore. Its successor, the James Webb Space Telescope, peers even farther, to the faint light of galaxies born just a few 100 million years after the Big Bang. Here, infinity is temporal. the attempt to see back to the origin of time itself. Each faint galaxy is a fossil, its photons traveling for billions of years. Each deep-field image is a portrait of finitude stretched against the suggestion of the infinite. But telescopes do not stop at light. The Planck satellite mapped the cosmic microwave background, the afterglow of creation. In its delicate fluctuations, scientists read the seeds of structure. The patterns match inflationary models, pointing toward an era of expansion so rapid it appears infinite in scale. Yet even Planck could not resolve what lay beyond. New missions, Light Bayard in Japan, CMBS-4 in the United States, aim to catch the faint signature of primordial gravitational waves, ripples from the first instant of expansion. If detected, they would confirm inflation, and with it, the possibility of eternal inflation, a cosmos budding universes without end, a glimpse of infinity, written in polarization patterns on ancient light. Closer to home, detectors listen for gravity itself. LIGO and Virgo, joined now by Kagra in Japan, have captured the faint tremors of spacetime from colliding black holes. Each detection is a message from horizons where densities verge on infinity. In the ring-down of merging black holes, relativity is tested in the most extreme conditions nature allows. For now, Einstein's equations hold, but the search continues for deviations, tiny shifts that might betray the onset of quantum gravity, the point where infinities should dissolve. Soon, a new instrument will join them. LISA, a space-based gravitational wave detector, its arms millions of kilometers long, suspended in the silence of interplanetary space. It will listen to lower frequency waves, tracing supermassive black hole mergers across cosmic history. With LISA, the machine expands into the scale of the solar system itself, reaching further toward the physics of infinity. Other searches turn inward. Deep underground, shielded from cosmic rays, stand vats of liquid xenon, cooled to cryogenic silence. Experiments like Xenont in Italy and Luxeplin in South Dakota wait for the faintest shiver of an atom struck by dark matter. These detectors are designed to reveal the invisible framework of the universe, the unseen structure that shapes galaxies. If successful, they may uncover particles that challenge known physics, bridging the gap between finitude and the infinities, predicted by theory. So far, they have seen nothing, but their stillness is profound. The longer they wait, the more they constrain, carving the possible from the infinite unknown. Supercomputers join the enterprise. On their silicon planes, scientists simulate universes, letting digital galaxies form and cluster across billions of years. These models test the role of dark matter, dark energy, and cosmic expansion. They allow physicists to compare infinite possibilities against finite observation. Simulations are themselves a paradox, machines finite in memory, yet able to conjure patterns that stretch beyond human lifespans. They are the mind's extension, imagining infinities to see what reality permits. Even laboratories create echoes of the extreme. Bose-Einstein condensates, clouds of atoms cooled to near absolute zero, can be shaped into analog black holes. In them, physicists watch horizons form and study the escape of phonons, sound-like particles in analogues to Hawking radiation. These tabletop experiments are not black holes, but metaphors made physical. They are miniature infinities, allowing scientists to study what cannot otherwise be reached. Each of these instruments is part of the machine. The collider, the telescope, the detector, the supercomputer, the analog experiment. Each probes a facet of infinity. Together they form a web of measurement, straining toward the unmeasurable. And yet, despite the grandeur of these tools, infinity slips away. The LHC finds no sign of supersymmetry. Dark matter detectors remain silent. Telescopes glimpse only part of the universe. Beyond the cosmic horizon lies unobservable vastness. Even gravitational waves, though miraculous, confirm relativity rather than expose its limits. The machine grows larger, sharper, more powerful, but the horizon of infinity recedes just as quickly. This raises a haunting question. Is infinity measurable at all? Or is it, by definition, forever beyond the reach of tools? Some physicists suggest that infinities are signs of mistaken assumptions, that reality is fundamentally finite. Others believe infinity is woven into the universe itself, inseparable from its fabric. The tools of science cannot yet decide. They can only push the boundary outward, inch by inch, light year by light year, particle by particle. Still, the pursuit is not failure. Every constraint narrows the infinite. Every non-detection refines what can be true. The silence of detectors, the steadiness of relativity, the limits of telescopes, each is a step closer to understanding what infinity means in nature. Perhaps infinity will never be measured. Perhaps the machine will only reveal that the infinite is an idea, not a reality. But in that revelation, there is progress. To prove that infinity does not exist in physics would be as profound as to prove that it does. And so humanity continues to build. Plans are drawn for the future circular collider, 4 times the size of the LHC, to push energies toward the Planck scale. The Vera C. Rubin Observatory will map billions of galaxies, measuring the acceleration of the cosmos with unprecedented precision. The Euclid mission, launched by ESA and NASA's upcoming Roman telescope, will probe dark energy, the silent force driving cosmic acceleration, stretching time itself toward potential infinity. The machine grows ever more ambitious. It spreads beneath mountains, across continents, into orbit, and soon into deep space. It is not a single device, but a civilization's collective enterprise, the expression of a species unwilling to accept ignorance. In chasing infinity, humanity has built its greatest mirror, a mirror in which it sees both the limits of knowledge and the unyielding desire to transcend them. The machine that measures infinity does not yet succeed, but it is already profound, for in its striving, it reveals that the human impulse is not only to live within the finite, but to press against its walls, to ask what lies beyond. The pursuit itself becomes a kind of answer. Infinity may be unmeasurable, but the act of measuring is infinite in spirit. Infinity has always lived at the edges of human thought. It waits at the horizon of vision, at the limits of calculation, in the silence where equations collapse into impossibility. For millennia, it was the province of mystics and poets, a concept, rather than a reality. Yet in the modern age, scientists built machines to chase it. They hurled particles together. They cast telescopes into orbit. They cooled atoms to silence. And they listened to spacetime itself quiver with gravitational waves. Each device became part of the great machine, humanity's attempt to measure the unmeasurable, and still, infinity remains untamed. The collider finds only silence where new physics was expected. Telescopes reveal only the observable, leaving the unobservable cloaked forever. Detectors lie in patient stillness, waiting for particles that never arrive. Simulations bloom and collapse in silicon landscapes, never quite matching the fullness of reality. The machine presses against the infinite, but the infinite withdraws. Like a tide forever out of reach. This is not failure, it is revelation. For the closer the machine approaches, the more it teaches about the meaning of infinity itself. Infinity may not be a physical property. It may be a mirror of thought, a mathematical construct born from the human impulse to imagine without limit. When relativity predicts singularities of infinite density, perhaps it signals not reality, but the breaking of the theory's domain. When quantum field theories explode into infinities that must be renormalized, perhaps they remind us that our equations are scaffolds, not the building itself. Infinity, in this sense, is a signpost, not a destination, but a warning that the map has ended. And yet there are moments when infinity feels more than a thought experiment. Black holes, whose horizons are carved by mathematics, seem to harbor infinities in their cores. The Big Bang itself emerges from equations that demand infinite density, infinite temperature, infinite curvature. If these infinities are illusions, they are illusions written so deeply into the cosmos that they shape galaxies, birth stars, and define the flow of time. Infinity may be a ghost, but it is a ghost with power. Philosophers once asked whether infinity is potential or actual. Potential infinity is the endless continuation, a sequence of numbers, a line extended without end. Actual infinity is total, an infinite completed whole. In physics, both haunt the landscape. Potential infinity appears in the unending expansion of the cosmos, the eternal stretching of dark energy that drives galaxies apart faster than light can bridge. Actual infinity appears in eternal inflation, where universes bubble endlessly from a primordial field, creating not just one cosmos, but infinitely many. Both possibilities are staggering. Both carry a sense of disquiet. For what does it mean if infinity is real? It means that every possible arrangement of matter exists somewhere, that every story is repeated endlessly, that every human choice is echoed in infinite variations. It means that the universe is not only vast, but unbounded, a library without walls. For some, this is a comfort. Nothing is unique, but nothing is lost. For others, it is unbearable. Individuality dissolves into endless repetition. Infinity confronts human meaning with both wonder and dread. And what if infinity is not real? What if the cosmos is finite, bounded, fragile? Then existence itself is rarer than imagination suggests. Every life, every planet, every galaxy becomes precious, not as one of countless repetitions, but as singular, unrepeatable. A finite universe makes each moment irreplaceable, each life a phenomenon that will never occur again. Infinity dissolves meaning into repetition, but finitude sharpens it, making it luminous against the darkness. Thus, the machine that measures infinity is more than a network of instruments. It is a mirror for the human condition. It reflects our paradox, creatures bound in finite bodies, with finite lives, dreaming of the infinite. The pursuit of infinity is, in truth, the pursuit of transcendence. In the halls of physics, there is unease. Infinities appear in calculations not as answers, but as breakdowns. They are the flare of error, the edge of known laws. To physicists, infinity is both guide and enemy. It shows where theories fail, but it prevents theories from being whole. The effort to resolve infinity is not merely technical, it is philosophical. It is the attempt to decide whether the universe is comprehensible at all. Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible. Infinity challenges that it is the reminder that perhaps the universe is only partly knowable, that human comprehension is not infinite, that the cosmos may extend beyond logic itself. And yet, even in this uncertainty, there is beauty. For to encounter the incomprehensible is to encounter mystery, and mystery is the wellspring of awe. Imagine, then, the closing image, a future astronomer standing beneath a thinning sky. Galaxies have drifted beyond the cosmic horizon. The stars above are fewer, dimmer. The machine that measures infinity still hums, telescopes scanning emptiness, detectors whispering silence, computers simulating universes that no longer can be compared to the sky. Infinity remains unmeasured. Yet the astronomer feels not despair, but reverence. For the pursuit itself, the act of asking what lies beyond the horizon, is the essence of being human. Infinity will not be captured in a detector's flash or a telescope's image. It will not be reduced to data points or equations. It will remain the horizon itself, the line that recedes as we approach, the silence that deepens as we listen. But in chasing it, humanity discovers something greater than infinity, its own capacity for wonder. For perhaps infinity is not out there. Perhaps it is within. It is the infinite reach of curiosity, the unbounded stretch of imagination, the endless layering of questions upon questions. The machine that measured infinity is, in the end, the human mind, extended by glass and steel, by mathematics and code, by dreams that refuse to accept limitation. And so the story closes not with an answer, but with an image, the cosmos as an ocean, stars as its surface foam, and infinity as the horizon beyond sight. The ships humanity builds, colliders, telescopes, detectors, sail toward that horizon, knowing it will never be reached. Yet they sail all the same, for it is in the sailing, not in the arrival, that infinity reveals its meaning. Infinity is unreachable, but wonder is eternal.